We've now built structure models, including class models, that lay out the structure of the information items that we want to work with. So now we're going to move toward building a database. So if we think about a database, it's basically a collection of related items. Most modern databases are in an electronic format, so we use what's called a DBMS, a database management system, to manage that database. We've got three basic types of database models. The most prevalent one used nowadays is relational. Relational databases use set theory and relation theory to structure all the information in the database into two-dimensional tables with relationships between them. Some of the older types of databases you might run into, hierarchical. These were the prevalent database types for mainframe systems up until the early, maybe even the mid to late 80s. But you're going to see a lot of mainframe systems still running on these, especially a lot of large company critical applications, back office applications that there's been no need to update. Hierarchical, as the name suggests, is tree-like structure like you would see in a taxonomy that defines parent-child relationships between all of the information elements in the database. The third type, and this came into play toward the latter days of hierarchical databases, is a network database. So network databases were put in place again on the mainframe for the most part and were gaining in popularity until the relational model came along. So network had a very short period of popularity. It's unlikely that you'll run into very many of those, but you might bump into one occasionally at one of your clients. The network model was designed to be a little bit more flexible than the hierarchical, that allowed you to define relationships, and in a lot of ways it had capabilities of a relational model, but it wasn't nearly as flexible as the current relational model is. You had to basically rebuild the database anytime you wanted to change the structure, whereas relational databases allow you to do a lot of that work on the fly. One of the keys for a network database model was that every record in the database could have different parents and childs, whereas the hierarchical database, every record is only going to roll up to one parent. And each parent, of course, can have multiple branches, so multiple children. So the hierarchy would be, parent, and then child, and these could also be broken down into lower and lower levels of detail. The network allowed a little bit more flexibility in linking information together. You didn't have to have all the tables related, so you'll see we left one off here in this example, but the tables could have multiple relationships. Both of these types, hierarchical and network, require relationships must be formed at creation, at database creation. Now the relational model is dominant now. Almost every enterprise system you're going to run into, unless it's relatively old, is going to be based on a relational database. Key advantages: well, it's a lot more flexible. You can add relationships, modify relationships without shutting the whole database down and rebuilding it. So that's one of the biggest advantages that relational databases had. You can incorporate a lot of logic and even programs into the database itself. And it's also a little bit easier to scale than the older style databases. So if you had to grow your database to utilize more space, you can again add storage to an enterprise relational database on the fly without shutting the entire database down, whereas that would be impossible on a hierarchical or network database. So the relational model is fairly simple in use as well. Pretty simple to understand. And implement. We can look at a relational database model and understand the nature of the various classes of information, the tables of information, fairly naturally compared to looking at a network database model or a strictly hierarchical model. Another advantage is relational database allows for better reduction of data redundancy. So in previous discussions we talked about database normalization. Normalization is something that requires the relational database model to work most effectively. So the relational model allows for this reduced redundancy and is another reason why it's the most widely used model in place today. Let's look at a few key database terms. First, we have the DBMS. So the database management system is the software, basically the computer program or the set of computer programs that manages all database activity. So that includes defining space for the database, creating the tables in the database, creating all the links between the tables, the relationships, adding the fields to the database, defining the rules regarding what can go into the fields in the database, all of that, adding data to the database, extracting data, deleting data, asking questions and reporting about information in the database. All that's done in the DBMS. The next term is data dictionary. And basically what we're doing in the data dictionary is defining all the fields used in the database. Now for some of the simple databases we're going to build, a data dictionary isn't all that important, but when you think about large databases running giant enterprise systems that have thousands of tables and even more thousands of fields to keep track of, it can become unwieldy in a hurry. For example, a property management system I worked on at ARCO had, for one piece of property, many different dates associated with it. Each of those dates played a role in allocating income, allocating expenses, allocating ownership shares for developing K1s and distributing revenue streams to the various owners. Each of these dates, even though they had very similar terms to them, had to be described very accurately to determine what is this date going to be used for. And we're not just talking 2 or 3 dates, we're talking about 15 to 20 dates associated with one piece of property and one activity involving that property. So the data dictionary helps describe everything. And who gets to manage that? Well, we've got a DBA, the database administrator, who manages the database. They're going to manage the data dictionary, help with the design, the implementation of the database, and just to keep it running and do any troubleshooting on it. Not a bad career path. My next door neighbor in Tampa, they had a pretty nice house. He was a DBA for what's now Verizon and seemed to enjoy his job quite a bit. Relational databases. Let's go ahead and start converting some of the UML modeling information we've put together into the databases themselves. So let's think about entities and attributes. So we take the UML class, and remember, using the REA model, that could be a resource, an event, or an agent, person associated with the activity, the event itself, the resources that are used in the activity, and these will turn into the tables. So the class, for the most part, becomes the tables. The attributes are going to lead us to the actual fields in those tables. And in true database lingo, you might hear these called columns. So basically it's a column in the table, if you think of your Excel spreadsheet. So these are going to be the characteristics of the table, and it can be also information about the columns. So we're really getting into metadata here, data about the data. So what are the characteristics? Is it a date column? Is it a number? Or is it a text-based column? Do we have any kinds of rules for it? So all of these are also attributes, the information about those columns. So we talked a little bit about the tables. And if we go back to set theory, these would be defined as a relation in the set. So this is the primary construct, if you will, of a database. The tables are where we're going to store data in a format that looks a lot like a spreadsheet. And each of these tables will represent a class from our UML class model or some kind of a relationship between those classes. Tables will be linked. As defined in class model. All right, so we've got tables. Next, within those tables, we talked about the columns. Those are the fields. Again, these represent the attributes of each piece of data that's going to go into the table. And then the rows and in set theory, these would be called tuples. In everyday file management lingo, we would call them records. So the rows represent instances of a class. So basically individual items within that class. If we have an employee class, well, we're going to set up an employee table that has lots of fields describing information about employees, and then we're going to have one row for each individual employee. In databases, we use keys to create the relationships between tables. And as we've talked about already, primary keys are important because they create a unique identifier for a specific row in a table, for a specific instance of a class. Foreign keys are going to be used to help create those relationships and allow us to link information from one table to the primary key in another table. So let's walk through an example of how that might happen. So first, let's take a look at a typical invoice form we might send out to one of our customers. Well, the first thing to look at is, okay, we've got some invoice information. We've got the date, we've got the invoice number, all that information. We also have information about our customer. And finally, we've got information about what is being ordered in this invoice. So, generic invoice information in red, customer information in the blue, and then the actual transaction information for the invoice in green. And now let's go to our information that we have in the database. We've got a sale and we've got an invoice number, and that was 13131. So we've got our invoice number, and then we've got our customer ID, which we see here is a foreign key, and that relates to the primary key here, customer. So we're going to make that link. Between the tables, customer ID to customer ID. So we've now related a sale in our sales table to one of our individual customers. And you can see here it's that to Wagstaff. Now we are also identifying which product is bought in this order. So we've got a product in the sale, and we see that that also is a foreign key related to the primary key here, and we can also see it relates to that particular Apple iPhone 5G. Is there such a thing? Well, we'll just pretend there is. Now we'll create that link between those tables. So this way we've got an efficient set of data. So we've got products stored independently here. We've got sale information stored independently here. And then we've got our customer information stored independently here. And then we build relationships in the database to link all those together for the business events of interest. A couple of the things we want to keep in mind when setting these relationships up are some of the requirements. First one, entity integrity. What does that mean? That means every primary key must have a value. Entity integrity. To maintain the integrity of the definition of that entity, we need to have some identifier for it. So the primary key has to have a value, can't be null. The next one is referential integrity. And you'll see this one in Access when you set up your relationship. And basically what that says is the data value used in a foreign key must match the related primary key, or a primary key in the related table. In other words, I can't set up, in my previous example, let's take a look at that real fast. I can't set up a new sale for a customer that doesn't already exist in the customer table. I can also not set up a sale for a product that does not already exist in the product table. Data value used in a foreign key must match the primary key in a related table. Now there's a variation on that that says you can have a foreign key left null to be filled in later. So that's a possibility that you can set up in a database. In practice, for the most part, you're going to see that we want to have that foreign key populated and also linked. Final set of table requirements. Each attribute has to have a unique name. So each attribute must have a unique name. Values within an attribute must be, getting ahead of myself, same value or same data type. So I can't have a date field for one record and then a text field for the next record. Any date field, if I've got it defined as a date, would have to continue to have a date data type. And that's important for calculations that are going to be made and queries that would be made and additional computer processing that's going to be done with that data. Each attribute must contain a single value. So basically each column or each field that we have in a record is going to have one piece of information in it. Now it could be a long string of text, that's fine, but it's going to have one piece of information in it as far as the database is concerned. And that's important when we consider how we're going to set up the relationships. And then from a normalization standpoint and data redundancy, you want to make sure that non-key attributes only define characteristics that are identifiable directly to the primary key. So in other words, when we have information in the database, we want to make sure, in our table, we want to make sure that that information refers back directly to the primary key. And let's take a look at our example once again. Look at the customer table. All of that information that we have there, their last name, first name, customer address, is directly identifiable to the customer ID. We would not want to put products purchased in the customer table because that we can identify with the sales table and the information in the sales table and the product table. So the product that would be purchased would go into the sales table. The name of that product that is purchased would go into the product table. So that's an important consideration and certainly one of the key components of normalization. Well, that's it for discussing database design and attributes. Now let's get started building one.